What if the most permanent solution to climate change has been sitting under our feet this entire time? Underground, right now, carbon dioxide is being pumped deep into the earth and turned into stone. Not stored, not contained, transformed permanently, at the molecular level. A gas that's destabilizing our climate, becoming rock that will outlast every building, every civilization, every species alive today. Most people have never heard of it. The ones who have can't stop thinking about it. It's called carbon mineralization. Carbon dioxide reacts with minerals in certain rocks and becomes carbonate stone, the same chemistry behind limestone, chalk and marble. And it may be the most durable carbon removal pathway we know how to do at scale. Which raises a strange question: if turning carbon dioxide into stone is this effective, why isn't the world doing it everywhere? That question will drive everything that follows. And the answer is more surprising than you'd expect. In the world of carbon removal, one question overrides everything else. How long does the carbon actually stay removed? Sounds like a technical detail. It isn't. It's the whole game. Forests can store carbon for decades and then release it in a wildfire. Saline aquifer storage is promising, but it still requires long-term monitoring and carries some leakage risk. Mineral carbonates are in a different category entirely. Limestone, chalk, marble. All carbonates, the same material that built the Egyptian pyramids and the white cliffs of Dover. Stable on the surface of this planet for tens to hundreds of millions of years. Under normal conditions, they simply do not break down and release carbon dioxide. When carbon dioxide becomes rock, it's gone. Not for a century, not for a millennium, for geological time. Carbon dioxide levels are higher today than at any point in the last 3 million years. And here's the part most climate coverage glosses over. Even if we stopped every emission tomorrow, the carbon dioxide already in the atmosphere would keep warming the planet for centuries. The gas we've released isn't going anywhere on its own. Two distinct problems then. 1. Stop adding more. 2. Remove what's already up there. Carbon dioxide removal, the second half of the climate problem, is where most approaches fall short. Trees burn, soils get disturbed. Engineered geological storage needs monitoring. Most carbon removal methods can remove carbon dioxide. Far fewer can lock it away for geologic time. Here is the simplest version of what happens. Carbon dioxide dissolves in water. That acidic water reacts with certain rocks. The rock releases calcium or magnesium. Those elements bind with the carbon and form solid stone. That stone is stable for millions of years. This reaction is one of the most fundamental processes on Earth. Scientists call it the carbon-silicate cycle, the planet's own long-term thermostat. When carbon dioxide gets too high, weathering accelerates, more carbon gets locked into rock and levels come back down. 4 billion years of keeping Earth habitable through solar variation, continental drift, and every mass extinction in between. Naturally, this takes thousands to millions of years. The engineering challenge, the entire challenge, is acceleration. Doing in years what geology does in millennia. 3 pathways exist for doing that. First, inject carbon dioxide underground into reactive rock and let the geology do the work fast. Second, crush silicate rock into powder and spread it on farmland, letting natural processes drive the reaction at accelerated rates. Third, use industrial waste streams as the reactive feedstock in controlled carbonation environments. Each is real, each is being deployed today, and each has its own story. The first story starts with a question that puzzled scientists for decades. They knew the chemistry worked. They knew basalt, the black volcanic rock that covers most of the ocean floor and large swathes of every continent, was rich in exactly the minerals that react most readily with carbon dioxide. They knew that if you could get carbon dioxide into contact with basalt underground, it would mineralize. What they did not know was how long it would take. Every model said decades, some said centuries. The uncertainty was the obstacle. In 2012, a team from the University of Iceland, Columbia University, and the University of Toulouse decided to stop modelling and start measuring. The project was called CarbFix, and it was run out of the Hellisheidi geothermal power plant outside Reykjavik. Geothermal energy produces carbon dioxide as a byproduct despite being considered clean. The hellish Heidi plant emits it constantly. Rather than releasing it into the air, the CarbFix team was betting they could dissolve it into water, essentially making carbonated water at industrial scale, and inject it deep into the basalt where it would react and solidify. What they did not expect was the speed. Within 2 years, isotopic tracer analysis, a technique that tags the injected carbon dioxide so scientists can track exactly where it goes, showed that more than 95% had converted to solid carbonate minerals. Published in Science in 2016, the results stunned the field. Not decades, not centuries. 2 years. Iceland's geology had created near-perfect conditions: fresh reactive basalt, warm groundwater, the right mineral chemistry. The carbon dioxide had not drifted or leaked. It had become rock. The implications were immediate. Basalt underlies roughly 70% of the ocean floor and vast continental formations on every inhabited continent. Enough rock to mineralize thousands of times more carbon dioxide than humanity has ever emitted. CarbFix has since scaled substantially. Its injection infrastructure became the geological backbone for Climeworks' Mammoth plant, the world's largest direct air capture facility, which pulls carbon dioxide straight from ambient air and sends it down CarbFix wells to mineralize underground. Mammoth is designed for up to 36,000 tons per year and is still in operational ramp-up, working through the engineering challenges any first-of-a-kind industrial facility encounters. The next milestone is the first megaton-scale facilities now breaking ground in the US and Middle East. The CarbFix story answered the question scientists had been asking for decades. The chemistry is fast enough, the geology is available, the proof of concept is solid, literally. But Iceland is one kind of geology, one kind of scale, one kind of cost. The second pathway works differently, and it starts somewhere you would never expect: a struggling farm in Brazil. The second story starts in a field in Brazil, and it begins with a problem that has nothing to do with climate change. Large parts of tropical South America sit on deeply weathered, acidic soils. The pH is wrong for most crops. Farmers have historically added lime, calcium carbonate, ground limestone to neutralize the acidity and make fields productive. It is a practice that goes back centuries. It works, but it is expensive, it has to be repeated, and it does not scale easily to the smallholder farms that feed much of the region. In the early 2010s, a group of researchers began asking a different question. Instead of adding calcium carbonate to the soil, what if you added the raw silicate rock that calcium carbonate is made from? Basalt, dunite, olivine. Rock that would weather slowly, continuously releasing calcium and magnesium, buffering acidity for years rather than months, and in the process absorbing carbon dioxide from the atmosphere as it reacted. The idea was called enhanced weathering, and the results from the Brazilian trials were striking. Yield improvements of 10 to 20% on previously acidic soils, sustained pH buffering, and measurable carbon drawdown, carbon dioxide pulled from the air converted to bicarbonate ions, flowing through soil into rivers and eventually into the ocean, where it joins Earth's marine carbonate system and remains stored for millions of years. Same chemistry as CarbFix. No injection wells, no industrial equipment, rock dust, rain and time. The farmer spreading crushed basalt at dawn is not doing something new. The practice of amending soil with minerals is ancient. What is new is the understanding that in doing so you're also running a carbon capture operation, one that uses existing farm equipment, existing supply chains, and produces a co-benefit the farmer already wanted. Several companies are now deploying this commercially across 3 continents. Because it leverages infrastructure that already exists, 2025 and 2026 pilots are hitting $160 to $220 per ton, a fraction of what direct air capture costs. This is what cheap mineralization looks like as it arrives. The scale potential is real. Deployed broadly across suitable agricultural land, enhanced weathering could eventually remove hundreds of millions to several billion tons of carbon dioxide per year, depending on assumptions, geology, and adoption rates. The central remaining challenge is measurement. Unlike the traceable injection of CarbFix, quantifying how much carbon dioxide has been captured requires tracking soil and water chemistry changes across entire farms. That science is maturing. In 2024, the European Union adopted its carbon removal certification framework, the first regulatory structure designed to answer not just does this work, but is the math honest? The specific methodologies for enhanced rock weathering are still being finalised. The question has shifted from whether mineralization is real to whether the accounting is trustworthy, and without credible measurement there is no carbon market to fund the scaling. The third story moves from the field to the factory floor and begins with a question a chemist named Cody Finke asked himself in 2019. Why does making cement have to release carbon dioxide at all? Portland cement, the binding agent in virtually all concrete, is made by heating limestone to around 1,450 degrees Celsius. That heat drives off carbon dioxide from the limestone itself. It is called a process emission, and it is unavoidable in conventional cement chemistry. Cement manufacturing is one of the single largest industrial sources of carbon dioxide on Earth. Every building, every road, every bridge built in the last century has this carbon cost baked into it. Finke's answer was to change the feedstock entirely. Instead of limestone, calcium carbonate, which releases carbon dioxide when heated, use calcium silicate rock, which does not. The heat drives a different reaction. The byproducts include magnesium oxides that, when exposed to air, slowly absorb carbon dioxide passively. The result is a cement with a fundamentally different emissions profile and potentially a net negative one over the lifetime of the building. That company is Brimstone. The Department of Energy selected it for major funding support in 2024, though that federal backing did not ultimately hold. Brimstone is pressing forward regardless because the economics of low-carbon cement, independent of any subsidy, are increasingly compelling as carbon pricing rises and construction industry decarbonisation mandates tighten globally. Carbon Built is taking a different angle, mineralizing carbon dioxide directly into concrete during the curing process. The concrete absorbs the gas and locks it into the structure permanently. Every block becomes a carbon sink. At steel mills and cement plants worldwide, mountains of grey waste, slag, fly ash, kiln dust and mine tailings already sit waiting to react. These materials are chemically similar to silicate rocks. They exist in enormous quantities. They are currently liabilities. With the right process chemistry, they become feedstock. We do not need a new industry. We already move more earth and stone for construction every year than for any other human activity. We need to point the existing one at a different goal. So back to the question planted at the start. The honest answer is one word: cost. Not chemistry, not geology, just cost. Everything else, the permanence, the co-benefits, the measurement, is largely solved or solvable. The single obstacle that stands between carbon mineralization and deployment at the scale the climate requires is cost. Direct air capture coupled with geological injection runs $600 or more per tonne today. Enhanced rock weathering is already at $160 to $220 per tonne in leading pilots. These are two different cost curves on two different timelines, and conflating them obscures how quickly the low-tech end is moving. But even $160 per tonne needs to fall further. Removing the roughly 7 to 9 billion tonnes of carbon dioxide per year that current estimates say the world needs to capture by mid-century requires costs to drop dramatically and deployment to scale at a pace that has no precedent outside the energy transition itself. Can it happen? Look at the trajectory. Solar power cost $76 per watt in 1977. It costs less than 20 cents today. That drop happened because of policy support, learning curves, manufacturing scale, and sustained investment over decades. Every one of those forces is now being applied to carbon removal. The United States Inflation Reduction Act created the first meaningful tax credit for direct air capture. The European Union Innovation Fund is backing enhanced weathering and industrial carbonation pilots. Early purchase commitments from Stripe, Microsoft and Alphabet have created a market signal that did not exist 5 years ago. Standards bodies are beginning to develop measurement frameworks for carbon removal. Investors are paying attention. Cost is the central obstacle, but it is not the only one. Measurement is the second challenge, specifically for enhanced weathering, where quantifying carbon drawdown across thousands of farm fields is technically demanding. The science of measuring it is improving, but not yet fully standardized. Until it is, carbon markets will remain appropriately cautious. Energy and logistics are real constraints too. Crushing rock, transporting it, drilling injection wells, all require clean energy inputs or the carbon math breaks down. Supply chains for silicate rock at billion-ton scale do not exist yet, but zoom out. 5 years ago, CarbFix was an academic experiment. Today, commercial mineralization projects operate on 4 continents. The technology works, the business models are forming, the policy frameworks are coming, the cost curves are moving. This is what the early innings of a transformative technology look like before it is obvious, before it is cheap, before everyone believes in it. The people building it believe in it now. History suggests they are right to. Something about carbon mineralization keeps pulling at me beyond the engineering. For billions of years, this planet ran a continuous carbon management system. Volcanoes released carbon dioxide. Silicate rocks absorbed it as they weathered. Carbon cycled through the ocean, the atmosphere, the crust. Over long timescales, that system kept Earth habitable through varying solar output, drifting continents, and every mass extinction in between. 200 years of burning, buried carbon disrupted it. Geological carbon laid down over hundreds of millions of years was released faster than any natural process could handle. Disrupted is the only word for it. Carbon mineralization is, in a deep sense, an attempt to re-engage with the system we broke. Not engineering around nature, but working with the chemistry Earth has been running for 4 billion years, consciously accelerating one of the planet's own carbon removal pathways, returning carbon deliberately and permanently to the rocks it came from. Volcanic basalt becomes calcium carbonate, carbon dioxide becomes stone. Something is right about that, not just chemically or strategically. Philosophically, we broke the carbon cycle. Mineralization is one way of helping Earth finish the job it already knows how to do. Not hype. Geochemistry. Carbon mineralization will not solve the climate crisis alone. Nothing will. Cutting emissions aggressively, restoring ecosystems, reinventing energy systems, and removing the carbon already in the atmosphere through every credible, durable pathway available, all of it is required. Of all those pathways, mineralization offers something singular: certainty. Certainty that what we remove stays removed, that the stone made today will still be stone a million years from now. We release buried carbon back into the sky. Carbon mineralization is one way of putting it back where it came from. Not in theory, in stone. Key papers and companies are linked in the description below. See you next time.